Okay, let's get started. Hey, first of all, any questions? Okay, so let's see what we covered in our last lecture. In our last lecture, we start talking about chapter 8, right? Hopefully we can finish it today. So in chapter 8, we mainly focus on the differential entropy and also all the relative information theoretic quantities. Okay, and we firstly talk about the differential entropy, and then we talk about the relative entropy, and the joint entropy, and the conditional entropy, right? So, okay, so let's see. So here is the definition of the differential entropy. So we derive it during the class, right? So basically, we derive the differential entropy from the entropy for the discrete random variables, right? Okay, so one thing to emphasize here is that the differential entropy is not a metric of uncertainty, right? So because we basically ignore a term, right? So the term will go to infinity, right? So basically, so we can now view the differential entropy as a measurement of the uncertainty, right? The other thing is that, so similarly to entropy, so now, we focus on some specific distribution. So one is the uniform distribution, right? And the other one is the Gaussian distribution. Okay, so those are basically the differential entropy, right? So for the discrete random variable, so we know that we have the cardinality bound, right? So we know the uniform distribution will maximize the entropy, right? But here, how about the differential entropy? So can we still say the same? Yeah, think about it. Yeah, why we cannot say that?
Well, it's just the support is like, well, for one, the support is a whole real number, or it can be a whole real number line, like with Gaussian, and then also it's a continuum. So
yeah, what if it's finite support?
it'd still be uniform line.
Yeah, think about that, right? So yeah, for differential, I mean, now we consider a continuous distribution, right? Things can be pretty weird. So we're going to see that in particular, so Gaussian distribution is somehow very special, okay? So we're going to see that. And okay, and then we talk about how can we derive the differential entropy, I mean the relative entropy, right? So here, so from the derivation, so we can observe that, so the relative entropy, so we don't need to change anything for the relative entropy, right? So basically, so when we derive it from the discrete random variable, so we do not need to do any approximation, right? So basically, everything is rigorous. So this is basically the definition of the relative entropy. So we still have the exact same meaning compared to the discrete case. Okay, so for differential entropy, for relative entropy, everything is good. Okay, so we don't need to worry too much about it. Therefore, for mutual information, so we can see that we have the exact same meaning as before. Okay, so now you may expect that. Okay, so now if you consider a communication channel, what's the channel capacity? Probably it is still the maximization over mutual information, which is true. Okay, we're going to see that later. Okay, so we define the joint entropy, the joint differential entropy like this, and the conditional entropy, differential entropy like this. Okay, and then we can define differential entropy, and then the mutual information. So, so one of the reasons that we want this form, right? So it's kind of artificial, right? So we ignore a term that we don't like, and then we get this term, right? So there are like a few reasons we want this definition. So one reason is that, okay, so from here, we can get differential entropy and mutual information. So they hold the same meaning, so which are good, right? The other reason is that if we define, define differential entropy in this form, so which is exactly the same as the discrete time entropy, right? So the benefit of that is, so all the property, almost all the property we have seen before will hold here, or all the identities. Yeah, property is not the right word to use because this can be less than 0, right? So all the identities we have seen before can work here because they have the exact same definition. Does that make sense? Yeah, most of the identities, of course. Okay, and here are a few remarks. So as we said before, mutual information have the exact same meaning, right? And all other information quantity can be defined similarly using the exact same method. Okay, and lastly, so all the identities for the discrete information quantity hold for different differential information quantities, right? So as we said before. Okay, and this is where we stopped in the last lecture. And today we're going to continue talking about this. Today is our lecture number 33, right? So I think we're going to have 39 lectures. There will be like 7 left. Okay, so hopefully we can finish chapter 8 today, and then we can talk about chapter 9 in our next lecture. Okay, first we're going to talk about the AEP for continuous random variables. And secondly, we're going to talk about the properties of the differential information quantities, okay? Yeah, let's see the first AEP. Okay, here there's nothing special, right? Because the definition of the differential entropy is exactly the same as before, right? The only thing we need to do is to replace summation by integral. Okay, everything else is the same. Therefore, we can use the exact same method to define the AEP, right? So, yeah, let's see. So as before, right, the first step is what? To define what is self-information, right? Self-information, definition of that is the same as before. So equals to minus log fx. Okay, so, and then, so the differential entropy is an expectation of this guy. Okay, so now be careful that, so it can be negative, right? Before we cannot have any negative numbers. Okay, and now, so in order to define the typical sequence, typical set, then we have to have a bunch of independent IID random sequence, right? So we have, let's say, that suppose that this guy is a sequence of IID. Why it disappeared? Continuous random variables. Okay, and then, so we just let a realization. What happened? Okay, x equals to x1 up to xn. Okay, and then, so we just do the same thing as before, right? We can compute the average self-information of that. Yeah, there's something wrong with my pen. So I cannot write. Yeah. What's going on? Yeah, there's something wrong with the. Okay, so this guy will equals to this. Okay, and since they are ID, so we can separate them, right? So basically, this will be sum over log fxi, I from 1 to n, right? So basically then, we let n goes to infinity, right? Clearly this guy will converge to the differential entropy in probability. Okay, so therefore, basically now we have the same definition as before. So we define for all the x as long as they are close, then so for those x, so they're in the typical set. Does that make sense? So exact same definition as before. Okay. So let epsilon bigger than 0, and then the typical set A epsilon n is defined as this guy, right? So now x is in all real numbers. So normally when we talk about differential entropy and so on, we just assume x will be all real numbers. And then so the absolute value between this and differential entropy is less than or equal to epsilon. Okay, if that happens, then we say, okay, so this is basic definition of the typical set, right? Which is exactly the same as before, right? Important thing here is that, so for those x has to be independent, RID, right? Then we can use the law of large numbers, right? So any question? Okay, so here we just focus on the IID case, right? So I think, so we can do something for the ergodic, stationary ergodic case, right? But here, we don't need to do that because one of the reasons is that we don't do a source compression for continuous random variable. Okay, we only do that for channel coding because in reality, yeah, for the source, normally what we do is that we do quantization and so on. Everything will be discrete, right? But for but for communication, so it's a totally different story, right? Because we need to transmit real signal over the air, right? There will be random noise adding on that. Normally, the noise can take any value. Therefore, we do have continuous random variable for communication we need to worry about. Okay. Okay, so for the properties, we still have the exact same property as before. So the first one is so basically with probability 1, I mean, the improbability, so the probability of the typical set is almost 1, right? So basically, when n goes to infinity, the probability that, so this typical set will almost happen, okay? And secondly, so what we have is the volume, or is the, so before, for the discrete case, we have the cardinality of the typical set. Right here, since it's continuous, so we talk about the volume instead of the cardinality, right? Okay, so yeah, here, so we let x in the typical set. Okay, then we let A is a subset of the real domain. Then we define the volume. It happened again. The volume of A is defined as, because it's continuous, right? So we don't talk about cardinality anymore, so we talk about the volume. So it's an integral over A, right? And then dx1, dx2 up to dxn. Okay, so that's the volume. Okay, so let's see this volume. Okay, volume of A. Okay, so now we use the volume to measure the, to measure the size of A. Okay, so now you can expect that, right? If the volume of A would be less than or equal to what, and bigger than or equal to what? Right. So basically, for the discrete case, so the volume or the cardinality of A will be less than what? 2 power of almost equal to 2 power of n times the entropy. Right here, the same thing. Okay, 2 power. Yeah, because we define the entropy and differential entropy in the same way, right? So you can do the exact same math to get it. So there's really no any difference besides switching the summation to integral. Okay, and then the lower bound would be very similar, right? So yeah, for lower bound, we need to be a bit more careful, right? We have 1 minus epsilon in the front to hx minus epsilon, right? So which is the exact same as before, right? And here we need to be a bit more careful. So upper bound will hold universally, but for the lower bound, so it holds for sufficiently large n. Okay. So any questions? Yes, this should be not very surprising, right? So everything holds as before. Okay, so we're done with that. So next, let's talk about the properties of the differential information quantities, right? So some of them are the same as before, but some of them is new, right? Let's see what are the same as before. First of all, the differential entropy between fx and gx. So this is bigger than or equal to 0. Okay, so which is the same as before because differential entropy has the exact same meaning, right? And with equality, if and only if f and g are equal. Okay, so here we just say almost everywhere. Right, meaning that as long as the probability is not 0, then they're equal. Okay. Or they can be not equal for some location that have a 0 measure, 0 probability or whatever. Okay, and so this is exactly the same as before. And the other thing is mutual information, right? So mutual information why is it always like that? What's wrong with it? Yeah, let me restart it. The mutual information is bigger than or equal to 0. Again, so when this equal to 0, with equality if and only if what? Do you remember? So when mutual information is exactly x and y are independent. Okay, very good. And the third thing is that, so we still have this conditional will reduce entropy, right? So the differential entropy x given y will be less than or equal to hx. Okay, and the proof, of course, is the same as before, right? So with equality, again, if and only if x and y are independent. Okay, very good. So yeah, so far everything's the same, right? Number 4 is still the same. So we have the chain rule, right? Let's see whether you can write it down yourself, right? So from x1 to xn equals to summation hxi given xi minus 1. Okay, chain rule is the same as before. So okay, next one, the independence bound. Okay, for the independent upper bound, we have this will be less than or equal to I from 1 to n hxi. Okay, so this is the independence upper bound with equality if and only if x1 to xn are independent. Okay, so we have 5 now. So far, everything looks exactly the same as before. So this basically means that all the tricks we studied before can apply here, which is good, right? So we don't waste too much. Okay, so number 6. So we have not seen that before. So it's called shift invariance. Okay, so this basically means that if we compute the differential entropy of x plus c, where c is a constant, what do you think? So will the differential entropy change or not? No, it will not change, right? Yeah. Yeah, because the distribution just shifts a little bit, right? So we don't change it, so this is kind of obvious. So the next one may not be extremely obvious, so it's called scaling. The scaling property, okay? Let's say, okay, so now if we compute differential entropy of A times X, where A is a constant, right, then what do we get? So will the differential entropy change?
Don't think so.
Why not? Yeah.
Because you're changing the variance, but not.
Yeah, we changed the variance, meaning the distribution changed,
Yeah, but
right?
there's not really a relationship between variance and or at least like variance is like your Euclidean sort of spread, but entropy just cares about the probabilities, and probabilities don't really change. They're just assigned.
It changed,
Yeah.
right? Because the variance changed, then then the distribution, the shape changed,
Yeah.
right? Therefore, yeah, this should be changed,
Oh,
right? Yeah. I think one way to think about that, you can think in terms of the discrete distribution,
Yeah, okay.
right?
Sure.
So yeah, although yeah, so the reason we say the differential entropy do not have the same meaning of the discrete case, it's artificial, right? We ignore a log delta in the end, right? If you add it back, right, then we still have this meaning, right? If you think in the discrete case, right? So if we multiply a constant in front of it, and then the shape changed, right? So if we multiply smaller a there, probably the shape will become more and more uniform, right? Then, yeah, so it changed a little bit, not too much. We add a constant term in the end. Okay, so yeah, I don't want to focus too much on the proof. You can take a look at the book, right? The proof is not that very difficult, so you can just take a look at that. Okay, and so this is a special case, right? It's a scalar case, but in practice, what we care about is the following, right? We care more about the vector case. Let's say if we let this, if this is random vector, okay, and then, so now let's consider what happened if we use a matrix to multiply this vector. Right, then what will be the differential entropy, right? Clearly, so this will equals to this guy, and then we'll have another term, right? So this is kind of tricky. So before, we just have absolute value of A here, right? But here, what we have is, can I take a guess? Yeah, because it's just a number, right? So it's not a vector. So yeah, before we have a log absolute value of A, and here, what should we have, right? What A will become? Take a guess.
Determinant?
Yeah, may not make a lot of sense, but it's a determinant of A, right? So all of you know what a determinant is, right? Okay, great. So we're going to see some examples. Yeah, this is kind of very important because later we're going to focus more on this case. Okay, so yeah, now we have number 7. So now number 8. Okay, so for number 8, we're going to consider the Gaussian random vector. Okay, so Gaussian is a very, very important case distribution when we talk about the differential entropy and the continuous random variable. Okay, so now let's see what is the differential entropy for the Gaussian case. Okay, so yeah, before that, we need to define what is a random Gaussian vector. Okay, probably all of you have seen that before, right? Did you? Some, okay. You have not seen that before, really? Okay, yeah. Let's define it, right? So definition is as follows. Yeah, so the key part is that in order to become a Gaussian random vector, the point is that it have to be jointly Gaussian. Okay, and individually it has to be a Gaussian, jointly it has to be a Gaussian. Okay, so let x1 till xn be multivariate Gaussian distribution. Okay, we assume that the mean is mu, so that's a vector, right? And so now, because we consider vector now, so we don't talk about the variance. We talk about covariance matrix, right? Covariance matrix, we denote that as K. Okay, so that will be a matrix, right, where K is the follows. So K is defined as a expectation of xn minus mu times xn minus mu transpose. Okay, so normally when we write a vector in this way, so that will be the, it's a column, right? And then this is a row, it's a column multiplied row, so it's a matrix. Okay, so very good. And so basically, we can, so for each element of this can be understood as follows. So basically, let's say if we denote this xi minus mu I square equals to sigma xi square, right? So basically that's the diagonal of the matrix, right? And then for the covariance, xi minus mu I times xj minus mu j, right? So we denote that as sigma xi xj. Okay, so then we can write down this matrix as the follows, right? So here is x1 square sigma x2 square up to sigma xn square, right? And then we have sigma x1 x2 up to sigma x1 xn. So here is up to, okay, here we can write one more term here, sigma x2 x1, okay, up to sigma xn x1, and so on. Okay, so this is a covariance matrix. Okay, and given the mean and the covariance matrix, right, and then we can write down the multivariate Gaussian distribution. So basically, in this case, the PDF is defined as follows: 1 over 2 pi n over 2 square root of determinant of k, right? And the exponential, e here is minus half x minus mu t k inverse x minus mu. Okay, so this is a joint multivariate Gaussian distribution. Okay. So any question? Okay, then let's compute the entropy, right? The differential entropy will be equals to what? Expectation. The expectation of log fxn, and we have a minus sign here. Okay, so let's compute that. So yeah, here, so this term is easier to deal with, right? So basically we have half n raised n over 2 and the square root of determinant of k. Okay, and we have a negative sign here, right? So here becomes a positive sign, n half log 2 pi plus 1 over 2 log determinant of k. Okay, yeah, those are this term, right? So this is relatively easy. Okay, so now let's see this term here, right? So we have minus sign here, then it cancels. We have a plus sign here, right? So here's add log e over 2, and then the expectation of this guy. K minus 1, x n minus mu. Okay? Yeah, we need to kind of compute this term, right? Which might be complicated. How can we compute that? So any idea? Yeah, how can we compute this? Okay, yeah, there's normally when you see this kind of thing, right? So we have, something very symmetric, right? X minus mu here, right? And we have something in the middle, right? So the only troublemaker is this k minus 1, right? This inverse matrix, right? If you don't have that, then it's not a big problem, right? But now the problem is that, right? So we have a normal trick to deal with that. So anybody seen that before? Yeah, from your random process class. Remember it?
Are you going to diagonalize it, or
Uh,
The trick is to assume it's identity matrix, and then you just go.
say again.
It,
Yeah, it is. It is. Yeah. So, but how do you prove it?
you just assume it is.
No, not assume. Yeah, we can compute it. Yeah, but the result is right. It's identity. Yeah. Okay. Yeah, we can show that. This is a common trick, but that's very good. I think you'll definitely have the right intuition. Okay. So basically, how we do that is as follows. So first, we have an important observation. So we're gonna do this. Let's do this here. Yeah. So yeah, let's do this here. So the first intuition here is that we observe. So this guy will equals to this guy. The trace of the same thing. So I mean, we just put that here. Does that make sense? Yes.
what is a trace?
Oh, what's the trace? Okay, very good. Yeah, let's see. Yeah, let's write it somewhere. Maybe I'll write it in the next page and then we'll go back. Okay, the trace of a matrix is the follows, right? So let's, for example, let's assume a matrix is like A11 up to A1n. Here is AN1 and here is ANN, right? So this is a matrix. A trace of it is just summation of all the diagonal value, right? Summation I from 1 to n, AII. So this is a trace. Okay, and clearly, so this equal to that. Is that clear? Yeah, because here it's only one number, right? So it's a horizontal. I mean, it's a row multiply matrix multiply column. So whatever is inside here is just a number. It's a scalar, right? Of course, you know, if we put a trace on scalar, it will be the itself. Right? So we can do that, right? Is that clear? Okay, then, so we have an important property of the trace. Okay, the trace of A times B, so their matrix, equals to the trace of B times A. Yeah, those are some property for the trace. Okay, so then basically we're going to use the same trick here, right? So now what we do is that we think this as an A and this as B. Okay, and then just switch them. Okay, then you get rid of, you know, the K in the middle, right? So that's basically the trick we use all the time. So this equals to expectation of the trace. So we'll write B first, xn minus mu. Yeah, so xn minus mu, yes. I don't want to use too many parentheses. And xn minus mu transpose. Okay. Right? Okay, very good. So now let's see. Okay, so basically you can see here are the random variables, right? And the k is not. K is deterministic, right? Then we can put the expectation inside, right? So basically now we have the trace of expectation of this guy, xn minus mu t, and then times k minus 1. Okay. Okay, then what did you find? So what is that? Exactly. What is that? Just k, right? Okay, then we have k times k. K times k inverse, right? And then, so basically that'll give you the trace of a identity matrix, right? And then that'll be n, right? So basically it doesn't mean that this guy is an identity, but the result is the same. Yeah, you have the right intuition. So very good. Okay, and then so this is n, right? So then so this will equals to what? So yeah, let me write it in the next page. It will be this one plus this one plus this multiply n, right? Okay, so okay, let's see. Interesting. Add one more page, so I will add one more here. Yeah, I'll do this here. So hxn, so we'll just equals to this guy plus determinant of k plus log e over 2 times n. Okay, and then we can combine all of them. So we have a half everywhere, right? And then we move everything inside, right? You can compute it. So basically, eventually, we're gonna have this 2 pi n determinant of k. Okay, so that's basically what we got. There's an e here, I missed. So this is the differential entropy of a Gaussian random variable, of a Gaussian matrix vector. Okay, so any questions? Okay, you can see an example in the book, so I'm now going to give you an example. So basically, hopefully you can finish the example offline. So basically, let's consider, so Gaussian vector xy have this kind of distribution. So sigma 1 square, sigma 2 square. Here we have rho, sigma 1, sigma 2, and rho, sigma 1, sigma 2, where rho is kind of the correlation factor, okay? And then compute, so what is the differential entropy and the mutual information, okay? Then what is the differential entropy, and then what is the mutual information? Right, compute it offline. So this should be pretty straightforward, right? So maybe one, so I said, this as k. So what is the determinant of k? Yeah, for a 2 by 2 matrix. Did you remember it? So it's a sigma 1 square times sigma 2 square. So the multiplication of this diagonal minus rho square, sigma 1 square, sigma 2 square, right? So it's minus, the multiplication of the off diagonal. Okay, so this multiply that minus this multiply that, right? So this is basically the determinant of a 2 by 2 matrix. Okay, very good. Okay, so we're going to continue. So just compute it offline. Let me know if you cannot do it. Okay, and yeah, the other thing is more interesting. So we're going to show, we're going to use information theory to help us to show some mathematical inequality. Okay, so that x1 to xn, so it will follow a Gaussian distribution, n and with zero mean and k covariance. Okay. So yeah, let's derive it and see what we can get. So basically, what we know is that, so we have this in independence upper bound. Okay, and now because all the x are Gaussian distribution, so we plug everything in and see what we get. Okay, so here basically for this term, so we know exactly what that is. It's log half log 2 pi e power n determinant of k. Determinant of k will be less than or equal to this. So here it's just a scalar, right? So basically scalar, we have seen that in our last class. Okay, and now yeah, let's move the summation inside and see what we can get. Okay, so basically what we can have now, so yeah, there's something, simplification we can do. So we can ignore this half. Okay, and when we move this n inside, so this can also be ignored. Okay, so basically eventually what we get is that the determinant will be less than or equal to the product from I to N. We have sigma xi squared. Okay, and that equals to a product of all the diagonal in the K. Right? Okay, so now we have a very interesting inequality, right? The determinant of K will be less than or equal to what? The product of all the diagonal values. Okay, so this is a mathematical inequality, and the point here is that we use the information theoretic approach to prove this inequality. So otherwise, it will be very difficult to prove. Does that make sense? So this is called Hadamard inequality. Wait. Okay, it's a pretty famous mathematical inequality. Okay, very good. Okay, next, let's introduce the next property. So maximum entropy inequality. Okay, so as we said before, so for the discrete case, we know the uniform distribution will maximize entropy. Right now, for the Gaussian, for the differential entropy, so what distribution will maximize the differential entropy? Yeah, of course, we need to have some different conditions, right? So basically, our constraint here is that, okay, for the random vector, let's say we have the same covariance matrix, okay, with the same covariance matrix, and then what distribution will maximize the differential entropy? Okay, let's write it down. For all random variables with the same covariance matrix K, the Gaussian random vectors the Gaussian random vector achieves the highest differential entropy. Okay, so this basically means that, so this guy will be less than or equal to 2 pi e n determinant of K. Okay, very good. So this is the result, right? So if we consider the same exact covariance matrix, then the Gaussian distribution will maximize the differential entropy, not uniform. Okay. Yeah, the reason we consider that is exactly like what Mark said before, right? So now we do not have the range constraint, right? But if we have the range constraint, right? Say okay, so now we fix from 0 to a, for example. Then what distribution will maximize the entropy? Still be the uniform? Yeah. But I don't care about that. What we care is, we do not have the constraint. Okay. So now the constraint is that if the covariance matrix are the same, then what distribution will maximize the entropy? So then the distribution will be Gaussian. Okay. So therefore, you can more or less think in this way. Okay. So the Gaussian distribution will have the most kind of uncertainty. Yeah, although we say okay, differential entropy does not have the exact meaning, but it sort of has, right? Because we just ignore a term there, right? Let's say we quantize it somehow, right? We sample it somehow and quantize it, right? And then it's kind of if we do not have the range constraint, so Gaussian will give you the maximum uncertainty. So that's intuition, which kind of makes sense, right? Because the central limit theorem, right? So if we add a bunch of things all together, right? Then this random variable will converge to a Gaussian distribution, right? Right. Therefore, it sort of means like Gaussian distribution will have the most randomness, right? That's why we like Gaussian distribution. Okay, I'm not going to show that. You can see how we show that in the book. It's very, very easy. Yeah, just only one-step trick. That can be very easy to understand. So now I'm going to introduce another inequality. So this is only for the differential entropy, only for the continuous random variable. Okay, we don't have that for the discrete case, and that can be extremely important. We don't use that a lot, but this can be very useful when we do proofs. It's called entropy power inequality. Okay, so yeah, let's derive it. See what do we mean by this. So basically, now we consider two random variables. Okay, so y follows a Gaussian distribution. Okay, and we let hx is less than hy, right? So equal to that. Okay. So we know that if x and y have the same covariance variance, then this inequality will be true, right? From here we can derive that this will be bigger than or equal to this guy. Okay, and this is called entropy power. Okay, so now we let x and y are independent, okay, and the Gaussian. Okay, and then, so what we have here is that, so yeah, let's consider the sigma of x plus y. Okay, so now we have a new random variable, so that is x plus y. Okay, and if x and y are independent, then what we get is this guy, right? We can see that, okay, so here, so yeah, because we assume they're Gaussian, then we have this inequality, right? So basically we know sigma and this will be equal. So this will equals to 2 pi e power 2 x h of x plus y, and this guy equals to this, and this guy equals to 2hy. Okay, and we know Gaussian will maximize entropy, right? But we say, okay, so now if x and y are not Gaussian, okay, and then what will happen, right? If x and y are not Gaussian, this guy will be bigger than or equal to this and that, right? So basically, I say if x and y are not Gaussian, and then this guy will be bigger than or equal to this and that. Okay, so this is called the entropy power inequality. Okay, again, so this is we only have this for the continuous random variable, right? Not for the discrete ones. Okay, and okay, still have 1 minute. Also, let's see. Okay, so let's finish it. So the last property that we're going to have is as follows. So we can use the differential entropy to have the mean square error bound. Okay, so if we let x hat be an estimate of x, right, then we can show that the expectation of x minus x hat. Okay. And let's say if this is a Gaussian, then there will be this is a variance, right? Then it will be sorry. So I mean if this is so this clearly that is a variance, right? So then it will be larger than or equal to this guy. Okay, so this is the first part, and so this is like we do not have any constraint, right? So if we just estimate x and we get x hat, and then we can show this will be bigger than or equal to this guy. Okay, and however, in practice, so normally we cannot estimate x directly, right? So what we can do is that we observe a y, right, and then we estimate x from a y. Okay, and for that kind of estimation, so what is the lower bound for this mean square error? Okay, so now we assume that x and y be jointly distributed continuous random variable, and let x hat of y be an estimate of x from y. Okay, so basically here we assume this is the estimation of x from y, right? So now what we can show is that the error lower bound will be given by what? Can I take a guess? So now we estimate x from y, right? It will be similar compared to this, but now, so the exponent will be the same, will be different, right? It will be x given y. Okay, that makes sense, right? All of them use the property that we introduced before, right? So basically, Gaussian will maximize the entropy. Okay, so you can see how we prove that in the book. So it's pretty straightforward proof. Okay, so I think we're going to end for today. And from the next lecture, we're going to talk about chapter 9. Okay, so I'll upload a new homework today, so you can start doing this. Thank you.